Okay, our next unit we're going to study is called modern physics. And modern physics is physics from about 1900 on. Before that, people thought that the ideas that Newton had, Newton's laws, could explain pretty much everything. And there wasn't anything really new that people would be learning in physics. But right around 1900, they started observing things that Newton's laws could not explain, and our ideas of waves could not explain, and they had to come up with some new ideas. And it turned out that a lot of what they were seeing was very strange and hard to explain. And the only way to explain it was to come up with quantum mechanics. So modern physics is the beginning of quantum mechanics, and that's what we're going to be learning about. The first phenomenon that people started to study that they couldn't explain was called the photoelectric effect. And the description of the photoelectric effect is pretty straightforward. Photo means light. You have light hitting a surface. When it hits the surface, it's going to knock out electrons. So light hits the surface and knocks out electrons. Now, you see this in a couple places in real life. One way is in solar cells. Light hits the surface, knocks out electrons. Those electrons cause a current, and you can use a solar cell, say, to power a calculator. Another place is in photosynthesis. Light hits the chlorophyll, and it actually releases an electron, and then that causes the reaction of photosynthesis to occur. Now, any light won't knock electrons off of any surface. It doesn't happen all the time. It only happens, say, for solar cells. It doesn't work with most metals. So there is a minimum amount of energy you need to overcome to release the electrons. The electrons are bound in the solid with a certain amount of energy. And they call that energy the work function. So electrons are held in by a work function. We're going to use the symbol W0 for that. It's the minimum energy required to remove an electron. If the energy of the light is above the work function, then electrons will be emitted. So remember, energy and work are kind of synonymous. They're both in joules. The definition of energy is change. I'm sorry, the definition of work is change in energy. So they called this minimum energy the work function. So they wanted to start studying this, so they set up this kind of complicated experiment. They're going to have light hitting a surface. It's going to knock out electrons, and the electrons would fly across the gap here. So they're flying across the gap. They're going to hit this surface, and then they would go around this circuit, and you would read a current on this ammeter here. They put a variable power supply in there, and when the power supply is off, the electrons will just flow around. But if I turn on the power supply, this side of it is negative, and that's going to repel the electrons or push them back the other way. If I get the power at the right amount, I can actually stop the electrons. So we're going to take some notes on that here. Okay? It's used to measure the kinetic energy of the electrons. Okay? Light hits the surface and knocks out electrons, causing a counterclockwise current, which is what I was just talking about. Then, you're going to turn up the voltage, and that's going to resist the current. When the voltage is just right, the current's going to stop, and it's called the stopping potential. We'll call it V stop. Then, we have this equation W equals QV. Okay, so the work done is equal to Q, the charge on an electron, times the voltage. All right, and the work done is equal to change in energy. If I'm stopping them, they lose all their kinetic energy, so the kinetic energy lost is equal to that work done. So you use this equation to find the kinetic energy of the electrons. Now, when they started studying this, they found out some things that didn't seem to make any sense. Okay, the first thing is that there's a minimum frequency, a threshold frequency necessary to overcome the work function and knock out electrons, which kind of makes sense. The bigger the frequency, the more energy the light is going to have. So if you're at a high enough energy, you can overcome the work function. But the second part didn't make sense. Lower frequency light, no matter how bright, will release electrons. Even if the low frequency light has a huge total energy, it can't overcome the work function. So I'm going to kind of make a sketch of that over here. All right, I have my surface, okay, and I'll have, say, dim, very dim blue light. Okay, the total energy of this dim blue light is very small. Okay, because blue is high frequency. That's kind of higher energy, but it's so dim it has almost no energy at all. And it hits the surface, you overcome the work function, and it knocks out electrons. Okay? But then you have very bright red light. Okay? It has a huge total energy. Okay? I have the same surface, so it has the same work function. I have this giant red light hitting it, big powerful laser, okay? And no electrons come out. And they couldn't understand that because they knew you have to have enough energy to overcome the work function, but this bright red light has way more energy than this dim blue light, and yet it's not overcoming the work function. So they couldn't figure out what was going on, okay? And the explanation came from Albert Einstein. He took the work of a guy named Max Planck and expanded it to explain the photoelectric effect. And he came up with some ideas. Light comes in particles called photons. So instead of being a wave, light is a little particle, okay, a little chunk. And the name of that particle is a photon. The energy of each photon is related to its frequency. That makes sense. Higher frequency light is going to be more energy. Okay? Now, there's an equation he came up with. The energy is equal to hf. Okay, F is the frequency, and then h is Planck's constant. Now, if you want your answer or you have information in joules, you use the top version of it, 6.63 times 10 to the minus 34th. If you want your answer or you're given information in electron volts, which is another energy unit, you're going to use the other version of Planck's constant. Now, another way of looking at it is hc over lambda, because the frequency would be velocity over wavelength. Velocity is c. So there's two ways of writing this. Okay, we can do E equals hf, or we can do E equals hc over lambda, depending on what you have. The hf is in the reference tables. The hc over lambda is not. Okay, our next little piece. Okay, now, here is where it starts to explain the photoelectric effect. Electrons can only absorb one photon at a time. And the brightness of it is equal to the number of photons. Okay, so now we have to start thinking about this. Light is no longer a wave, it's a particle. Brightness is no longer amplitude, it's number of particles or number of photons. I'm going to draw a sketch down here to explain why this works, how this explains the photoelectric effect. So let's have our work function, okay, or our surface, and let's say the work function is 8 EVs. Okay, so I have my light coming in has to have at least an energy of 8 EVs in order to be able to knock out an electron. Now, I'm going to have dim blue light. Okay, so here's my blue light. Okay, this is one photon, so it's very dim. The brightness is the number of photons. This is just one single little photon. Okay, so it's very, very dim. All right, but that photon has an energy of, let's say, 12 EVs. It's related to the frequency. Blue light is high frequency, so it's going to have quite a bit of energy. Are electrons going to come out? And the answer is yes. Electrons in this case are going to come out, and like so, because the energy is above the work function. How much energy is left over? Well, it turns out there's 4, and that since energy conserved, it has to go somewhere. It goes into the kinetic energy of electrons. So the kinetic energy of these electrons is going to equal 4 EVs. Now, let's look at, so let's label this. I didn't label it over here. This is dim blue light. Okay, it's dim, yeah, it's dim blue light. Now, over here we're going to do bright red light. All right, so we'll use the same surface with the same work function. Okay, Now, if it's bright, it has lots and lots and lots of photons. So we're going to draw, say, 3 photons. Okay? But since it's red light, each photon is going to have less energy. So let's say that the energy for this one is 6, for this one is 6, and for this one the energy is 6. Okay? Now the electron that's down in the surface is going to absorb, say, one of these 6 eV photons. All right? Is that enough to overcome the work function? No, it's less than 8, so it can't. And it can't absorb all 3 of them. It can only absorb them one at a time. So the most energy it could gain is 6. It can't overcome the work function. So in this case, we're going to write that there are no electrons that are emitted because the energy of each photon is less than the work function. My E total, I want to make a note of this, my E total is equal to 6 plus 6 plus 6 is 18 EVs. So I have lots of total energy, more than the work function, but it can't knock it out because the energy comes in particles and the electron can only absorb one particle at a time. So I said they started to find out some weird things at the beginning of quantum mechanics. What they found out is that light, which they always thought of as a wave, when you're doing the photoelectric effect, it has to be a particle in order to work. Now, top of the next page, we have a mathematical example, okay, and then we're going to talk about why it's important. So I'm going to write down our equations, maybe up at the top here, just so we have these handy. I usually use a little gamma symbol to mean a photon. So this says the energy of a photon equals HF equals hc over lambda. And h is 6.63 times 10 to the minus 34th joule seconds, or 4.14 times 10 to the minus 15th EV seconds. We're going to use one or the other version depending on what units we want in the problem. Now it says photon of light with a frequency of 6 times 10 to the 15th hertz strikes a photoemissive surface with a work function of 20, and then it breaks up the problem. So I'm going to sketch this. I always like to do a sketch with these problems. So I have my surface. I have a work function of 20 EVs. I have light coming in, like so. Okay, and this has a frequency of 6 times 10 to the 15th hertz. Okay, now these always end up being conservation of energy problems. All right, I have to know, is the energy of this light coming in great enough to overcome this work function? Then I'll know if electrons are released or not. So I need to find the energy of this incoming light. So that's always what you're going to be doing, is finding energies. If they don't give you energy, you have to find energy. The work function's already an energy, so I don't have to do anything with that, but I have to find the energy of this light coming in. And that's what step 1 is telling me to do. They may not give you step 1. I was trying to lead you in this particular problem. So the energy of the photon, I know its frequency, I'm going to use E equals HF, this equation right here. And I have to choose which version of H do I want to use. Do I want to pick the 6.63 times 10 to the minus 34th, or do I want to use the 4.14 times 10 to the minus 15th? Since over here I was given the work function in EVs, I want to use the one that's in EVs. Otherwise, I would use the one in joules, because most of the time our energy is going to be in joules. So if I'm given joules, I'll use a joule one, or if I'm not given units, I'm probably going to try to use a joule one. But if I'm given EVs, I'm going to use the EV version. So my H is going to be 4.14 times 10 to the minus 15th. My F was 6 times 10 to the 15th. And when I multiply those together, I'm going to find an energy of 24.84 EVs. Part 2. will electrons be released? So the energy of this thing coming in is 24.84. Can it overcome the work function? The work function is only 20, so yes. And then what's the kinetic energy going to be? Well, the light has 24.84 EVs per photon to give up. The electron is going to only take 20 to make it be released. The rest goes into the kinetic energy. So the kinetic energy of the electron is going to be 24.84 minus 20, which is going to give me a value of 4.84 EVs. Now the next step is a two-step problem, and it's kind of tricky. I want to know the speed, all right? So in order to find the speed of the electrons, I have kinetic energy, so I'm going to use KE is 1/2 mv squared, and that'll give me velocity. Now the problem is I'm in the wrong units, okay? I have 4.84 EVs, and I have to be in joules if I want to use this equation. So I have to convert. It turns out that 1 EV is 1.6 times 10 to the minus 19th joules. So if I want to convert this EVs to joules, I'm going to multiply by that 1.6 times 10 to the minus 19th. So I'll take 4.84 and multiply that by 1.6 times 10 to the minus 19th. And when I do that, I get a value of 7.74 times 10 to the minus 19th joules. Then I can plug that in here into my kinetic energy equation, and I get 7.74 times 10 to the minus 19th equals 1/2. Now it's an electron, so we can look up the mass if we don't have it memorized. It's 9.11 times 10 to the minus 31, then times v squared. And when I do that, I end up with a velocity of 1.3 times 10 to the 6th meters per second. So that was kind of a difficult problem, at least the third part of it. But remember, they're always conservation of energy, so you have to find the energy of the incoming wave, and then use that to see if you can overcome the work function. If you can, the leftover is the kinetic energy of the electron. Now, why is the photoelectric effect such an important thing? And we're going to say it's because it proves that light can be a particle. We always thought light had to be a wave. Einstein, what was genius about it is he figured out that light doesn't have to be a wave, it can be a particle, something nobody had ever thought of before. There we go. Okay, light has a dual nature. It can be a particle and it can be a wave. And here is the interesting thing, okay? So when light does interference, and diffraction, I can only explain that if light is a wave. Okay? If two particles interact with each other, they bounce off of each other. If two waves interact with each other, they have constructive and destructive interference. We've seen that light does produce constructive and destructive interference. We did the lab with the laser. We shined it through a diffraction grating. It bent around behind it, and then we got an interference pattern with central max, first order max, second order max, and minimums in between them. So that is proof that light is a wave because it did this interference thing. Okay, but when I'm looking at the photoelectric effect, the only way Einstein could explain it is if light is a particle. Okay, so that was a revolutionary idea, and like I said, it's the beginnings of quantum mechanics. you don't have to draw this, but I want you to think about it because this is kind of weird, okay? Let's say I have light coming upon a double slit. It starts to diffract behind each of those holes, essentially making two light waves. They start to interfere, and I get a central max, and a first order max, and another first order max, and I'm not going to draw it, but maybe a second order max, and so on. Then that light is going to hit a surface and knock out electrons. So here's my electron coming flying out. Label that electron. Okay. Now over here, as the light is coming up to the slits, okay, and it's going to cause interference and give me a central max, first order max, and so on, light has to be a wave over here. Okay? But then, when it hits this surface and knocks out an electron, light has to be a particle. Here's the odd thing, okay? How does the light know that at first it's, oh, I see two slits coming up, I have to interfere, I better act like a wave. And then, oh, over in the second part, I see a surface coming, I'm going to knock out an electron, I have to act like a particle. How does it change its nature like that? And that's something that really we can't really understand. Okay, maybe light isn't really a particle or a wave. Maybe it's something that can behave like both. So this is sometimes called the dual nature of light. Okay, light has two natures. It can be a wave or it can be a particle.